out. So now with that, I think we're going to get into the bulk of our meeting here. And I'm going to turn this over to Arlen Colby, who will be the person who will introduce our speaker. So with that, Arlen, would you unmute yourself and come to the floor and introduce Brian, please?
All right, good. I'm proud to introduce my friend Brian Sykes. I live in Barron, Wisconsin, and Brian grew up only 4 miles away, but I did not know him when he was growing up. He's a little bit younger than me, and I was teaching, coaching, etc. When he was chasing trains and talking to railroaders, I sure wish I would have known him at that time and got my interest in trains started a little bit earlier. But right now we are able to share a lot of interests through the internet, but he comes home, his folks still live in Cameron, so he's coming home frequently now, especially since the pandemic is slowing down, and we're going to do a lot more things together. So one of the things we've been doing is chasing a lot of abandoned old railroads, just learning about the railroad history. He's edited many of my books, and we're going to be doing some stuff together. In fact, we're having coffee tomorrow, and Sunday we're going to our train club meeting, and I think next we're going four-wheeling probably next week on an old railroad grade. And I'm really looking forward because every time I'm with Brian, I learn more about railroading. And when he starts talking signals, he's way over my head. So I'm really looking forward tonight, like I think the rest of us are. So let's turn it over to Brian and have him do it.
Thank you for that, Arlen. I appreciate that. Yeah, Arlen and I have been acquainted for quite a while. I've learned an awful lot from Arlen too. Believe me, he's got a lot of things to share. So thank you everybody tonight for being here. I appreciate everybody's attendance on what is probably kind of a dry subject. I'm going to try to make it as interesting as I can, but you know, it's and try not to get down in the weeds too far either, because there are a lot of things to cover here. I certainly would like to answer everybody's questions that you have, if there are any. And if we get through this and you didn't get your question answered, please get back in touch with me. I'll be glad to field questions later down the road at any time. Before we get started, one other gentleman that hasn't been introduced here tonight, I've got my friend and former coworker is in the house here tonight. John Marbury belongs to the Atlanta chapter of NHRS, and he's tuned in tonight because John is going to be making my presentation to the Atlanta chapter here in the next week or two. So I told him I recommend he be here tonight and to help him do that. So anyway, let's go ahead and get started here. I'll do the screen share here. Hopefully this works well. All right. So our first, my agenda tonight is to start, the title of my talk is The Communications and Signals Then and Now. We're going to lightly go over all the evolutionary changes that have occurred. I've got 9 different areas here I'd like to cover, starting with wayside signal systems. We'll go into grade crossings, locomotive and rolling stock issues, train crew communications, defect detectors, class yards, dispatch centers, train consist, and we'll finish up with PTC tonight. So let's get started. So I put up a slide of the pole line there. For probably 50 years or 80 years, very long time, the pole lines were the mainstay of the communication signal system. They carried just about, from the beginning, they carried just about anything that was CNS was going to ride on the pole line. So it was really a single point of failure, which was a bad news story. And which was the reason that during the last 50 years, there's been a lot of efforts to migrate off the pole lines, and you won't see that many pole lines out there on Class 1 railroads today. But the things that rode the pole line here, and I've got them in red highlighted, would be the signal type concerns, AC power, and that could be 110, 440. It could even be 4400 high tension you had in some areas, but the power came from the pole line. The top arms were usually the wayside signal controlled your aspects, yellow, green. You had the code line on there in a lot of places. Might control, 80 miles of railroad there has got the code line on it. You had crossing signal circuits broke across there. You had hand throw switch protection. So then you can drop down and talk about the communication side of it. And early on, you had the telegraph. Later, you had the VHF radios and voice circuits. Then in later years, you then had carriers, which carriers allowed. An example would be 28 circuits on a pair of wires. So that was a later technology on the pole line. Odd box detector circuits, And then we'll talk about Western Union, that some of you may be aware that Western Union used the railroad pole lines in some areas for the services that they provided. So one thing interesting about the fact that you've got C and S is that on a lot of railroads, the C and S departments were separate. You had a separate department for communication and you had a separate department for signals. And on some railroads, that meant that there wasn't one pole line, but there was two pole lines. I know on the Omaha between St. Paul and Butler, the communication was on the south side of the tracks and the signal was on the north side of the tracks. And that made for kind of an interesting, you'd always ask the question, why does the railroad have two pole lines? Well, two different railroad departments, two different pole lines. So we can start all here with the fundamental element of any signal system, whether it be wayside signals or the crossing signals, was the track circuit. And in the early days, the rail was jointed rail was used, a rail joint every 39 feet. That maybe on the surface didn't sound to be too bad would cause any problems, but bond wires had to be installed on every joint to allow the systems to work properly. And so that required those to be maintained. And there was a lot of things that could knock off a bond wire: vandalism, theft, dragging equipment. So to maintain all those joints out there, that was a big deal. And so starting in about the 1950s, you started to see continuous welded rail, and boy, was that a welcome relief for the signal maintainer to not have to maintain those bond wires. That really reduced a lot of maintenance, and it made the signal system and crossing signal systems a lot more reliable. At the end of each of those track circuits was an insulated joint, and in the early days, those insulated joints had to be maintained in the way of keeping the insulation in good shape. And in heavy traffic territories, that insulation would wear out because of the movement of the rail. So that those had to be changed out periodically. Oftentimes in heavy traffic, every couple of years, you're changing out the insulation of those joints to keep them from failing. So with the advent of ribbon rail came glue joint. And the glue joint, in theory, is a maintenance-free joint that's installed at the same time that the ribbon rail is, at the continuous welded rail. And in fact, in this picture, you can see the rail joint, the welds there, that joint is welded in place. And generally, that joint will probably last, even in high traffic density territories. That joint will last for the life of the welded rail. Until the rail wears down, that joint will be there. And so that's been an item that has really improved the maintenance and reliability of the signal system. Next, we can talk about batteries. All signal systems need batteries. All the track circuits need batteries, and the wayside systems run on 12 volts or 24 volts. In the early days, those batteries were glass jars, like you see here. And the maintainer had to periodically, what they'd say, build the battery. What does that mean? That means you put the plates in there, and then you pour the acid in there. Yeah, the signal maintainers had to deal with I think it was sulfuric acid, I believe it was. But anyway, they pour in the acid. So, they're dealing with hazmat, and you got to be very careful. The right-hand picture shows you the battery vault there with the glass jars that are going to go down in there after those batteries are built. A lot of railroads use concrete vaults to store these in. I know the Erie Lackawanna territory still out today, you can find those vaults out there, and most of them have been filled in, but they were like a big manhole, and the maintainers would have to climb down in there, and those were the batteries were down in those vaults. So batteries have gone through quite an evolution. The end result is what you see here. In this picture on the left is the sealed lead acid battery, which there were several evolutions to get to the final product, and you've got sealed lead acid today, and you've got sealed NiCads. But you had, for a while, you had nickel iron batteries. You evolved away from the glass jar batteries, and you evolved to a less maintenance battery that you didn't have to pour the acid in. You might have to pour some water in once in a while. And then the sealed batteries, you didn't even, in theory at least, you didn't need to water them. So it's been a big help to reduce the workload. Didn't have to lift them or change them out. Has reduced the maintenance workload. On the right, you see a DC to DC converter in a lot of control points today. instead of having a battery, you tap onto the 12-volt supply with a DC to DC converter, and you convert it down to 1.5 volts to become your track circuit battery. So in that sense, the battery is eliminated altogether. So that's kind of where you've gone to today. Like I say, the nickel iron or the NiCad battery today, I think, is what most of the railroads are going to. They're going away from the sealed lead acids was found. There's something the railroads tried, and they didn't last quite as long. They'd been used in the telecom industries for quite a while. The railroads tried them in the 90s, and I think the railroads are going back to NiCad now, or sealed NiCads. So for wayside signal control, the pole line again is the mainstay from going back to day one. The top arm generally would be the arm that would control the signal aspects, yellow, green, and you usually had 4 wires per track. So if you had double track, that would be 8 wires right there. So I should mention about pole lines that, common sense would tell you that they were high maintenance intensive, because when the bad weather comes through and the trees fall through the line, the maintainers are going to be out there. So they all had to be qualified to know how to climb poles, and it wasn't just done in good weather. They were out there in the middle of the night in the bad weather too, climbing these poles and putting these wires back up. So the improvements that we're going to talk about were very welcome improvements for the signal maintainer. He was able to be phased out of the climb and pole business. So one of the things that helped phase out the pole business was in the 50s, the signal vendors collaborating with the railroads figured out a way to have relays be used to pulse DC voltage onto the track. And in that fashion, depending on the pulse duration and the pulse widths, you could derive the signal aspects. A certain pulse rate would be for a yellow aspect, a certain pulse rate would be for a green aspect. No pulses would be a red aspect. So the signal companies figured out a way to pulse DC on the rails to allow you to then eliminate the need for line wires to carry the signal aspect information. So that was the first shot at eliminating the pole line, was with those systems installed in the 50s. They were usually coating relays, and of course they required maintenance too, but still it was much preferred to having open line wires out there. Other railroads used buried cable. The pole line was such a bad thing to have that, okay, well, let's bury cable. Let's put our pole line underground. So some railroads did that, particularly Conrail did that. So here's this piece of equipment right here is what really was the final answer to this, and that is electronic track circuits. And if you're around any signal railroaders, they'll tell you about electronic track circuits. Basically, what the relay systems in the 50s did, and that is that it pulses DC on the track, and you can derive the signal aspects from that. These systems came about in the late 1970s. A lot of skeptics out there. The old head railroaders would say, well, these will never work. All you're going to have is false proceed signals when you start using electronics. But no, that did not prove to be true. The electronic track circuits have really worked well, been a great success story. Microprocessors were introduced, going from discrete components to microprocessors starting in the mid-'80s. And these systems are what you use out there today with lots of great features, and we'll touch on some of them in a minute. So what about the signals themselves? Well, you see here the ball signal, okay, and on the Conway Scenic, you still have a ball scenic. You have a ball signal out there. The ball high in the air means go. The ball on low ball means stop, okay, and that most railroaders know that's where the term high ball came from, is going back to the high ball signals that used in the 1800s, or first signals that were used on the railroad. From there, the banjo signal came about, and the banjo signal, you might see some pictures around the turn of the last century, 1900. Those signals were able to display 2 aspects. I think it was blue and it was white, I think. I haven't seen a color picture to tell you for sure, but I know it was 2 aspects. So the banjo signal was next. And then after that, the semaphores came about. Okay, all of these in the early 1900s. And I think now there's just very few places in the United States where you can still find some semaphore signals out there on a wayside signal system. One of them, I think, was out in the Raton Pass area on the Amtrak route. There might still be some out there, but if you want to get a picture of them, you probably need to be out there doing that because they're on very borrowed time right now. You could have two versions of it, the lower quadrant or upper quadrant. This is the upper quadrant. That was probably the most common. The nice thing about semaphores that the train crews liked was that you could ascertain the signal aspect even if the lamp was burned out. You could see if it was a 9-degree clear or it was a horizontal red, restricted proceed. On the former PRR and on the NNW, you would see the position light signals. Some of them became, particularly on NNW, became color position light, not quite like the B&O, but they had red aspect in the horizontal. And then G heads were very popular. This is G head, and the transits, I say then, but you know, the transits are still using them. New Jersey Transit and SEPTA and others are still using the G head. And I mentioned the B&O signals, color position light. They were pretty unique. They've got the modifier lights up at the top, marker lights up at the top there that modified the for the different aspects. I'm not an expert on rule books, so I can't tell you what all of, you know, what a marker to the right means. I'm sure there's people on this conference call that can tell us what that is, but they were pretty unique, and it was really a lot of fun to, years ago when you could ride the dome car across from Pittsburgh to Washington, D.C., it was a lot of fun to watch those signals up there, and I think they're just about all of them are gone now. The searchlight was a popular signal. Mainly train crews liked them because they're probably the most, other than semaphores, they were the highest visibility of any when you're looking for an aspect. They had a lens in there, a compound lens that was about 2 inches thick, and you could see them, you know, 2 miles away in some cases. You could really see those signals, and they did well. But they were maintenance intensive in that there's a mechanism there, a signal mechanism in them that required testing every 6 months. So railroads now with PTC have been eliminating them, and the maintenance forces are kind of glad to get rid of them in favor of the D head. So the D head is right here. That's kind of become the standard now on all your class ones. And the hood is, they've gone from visors to hoods, mainly in the interest of phantom signals. Phantom signals where sunlight will shine in and into the inner lens, before they had LEDs. This is an LED you're looking at right here, but prior to the LEDs, the D head had it was a compound lenses in that you had an inner green, inner yellow, inner red with an outer clear. And a phantom would be where sunlight shines in and lights up, makes the inner lens look like it's lit. So that's the reason for the hood. But right here, this is LEDs. Not all railroads have gone to LEDs, but I think over time, you'll see a migration to the LEDs. This is a signal that you'll probably see out on the class ones here today, including the Canadians. And here's another now, and this is where in cab signal territory, particularly on former Conrail, signal indication point is what SIP stands for. That's defines the boundary of a track circuit in cab signal territory. So that's where an intermediate signal would have been or had been, but in cab signal territory where you did away with intermediates, you've only got signals at the control points. That's called a signal indication point. There'll be a bungalow there that will define that, so the train crew can know when it's going by a place where its cab signal aspect can change. Take just a second to talk about structures. You've seen a lot of evolution on structures. The early structures didn't have a lot in the way of fall protection, where the maintainer had something to hang on to when he was going up or down the ladders, and you had to really be careful, and they did. But this is an example too. On the old Southern, in the 1950s, when they went through the new signal system, they used boxcar center sills as the girder elements of these bridge signals. So they were bare bones for sure. An example of the signal department's frugality, I guess you'd say, of trying to do a lot with a little. That was a boxcar center sill you're looking at right there. The new bridge signals, you'll find that they have a lot of features of fall protection. Railroads don't strictly come under OSHA, but they are aware of the things that industry does in the way of to protect for fall protection. And you'll see those elements on the new signal bridges out there. They have the cage and places to tie off for fall arrest systems and the like. So code line, we mentioned about code lines in that was kind of the code line riding on the pole line was really the one that you worried about the most, because that pair of wires carrying the code line, if those wires were interrupted, that could knock out 30 miles, 50 miles, a lot more than just the HDs, a lot more than the yellow and green wires that I mentioned earlier. Yellow and green wires might only knock it out for 10 miles at the most, but these code line going out wires being tree through the line could mean that 50 miles of railroad was affected. And that happened quite a bit, to have, in a lot of areas, a tree going through the line at 50 miles of railroad. Yeah, that's not exactly a rare occurrence. So what did the railroads do? The railroads finally in the 90s, with the advent of wireless systems out there, developed as an industry, and this is an industry standard, allowed interoperability, which we'll talk about, the data radio, 900 megahertz data radio. So that's what you see here. The way the data radio works is the code for signal controls and indications from the dispatcher will ride over a data circuit out to a base station that's shown on the left, and there'll be a data radio transmitter at the base station. Will transmit 900 megahertz data packets down to the Wayside location shown in the middle. And those data packets contain the control and indication information for a control point. So a typical base station might talk to 5 or 10 control points and could carry that information. So it's done wirelessly. And so the code lines were no longer needed on the pole line or buried, anything else. There's usually double coverage, which meant that each control point could talk to at least 2 base stations. And where there wasn't double coverage, the railroads oftentimes would augment with cell phone backups. So the result was that where you used to have pretty frequent, or let's say not infrequent, code line outages today on the railroad are very rare, due to the use of I would attribute it to data radio. I don't know what the percentage is. Like I said, there's fiber optic and there's cell phones, there's other things out there, but I'm sure it's well over 50% of the control points, at least on the other than CSX, which uses satellites, which we'll talk about. Probably well over 50% of the control points out there are on 900 megahertz data rate, or 160 megahertz. UP uses 160 megahertz. And here's the satellite I mentioned earlier, being put in with PTC on CSX, so that when the 220 megahertz, this basically was an alternative to the CSX's use of 220 megahertz. So they use satellites to communicate with their control points for PTC information. And so they did not have to, and they used cell phones to communicate with the train. So they were able to greatly reduce the number of required base stations on their projects. Okay, so now let's change gears a little bit. Let's talk about interlockings. Historically, interlocking could be any number of type of installations. It could be a railroad crossing a grade. It could be an interlock junction, double crossover, end siding, any combination of those above types. And this term eventually in the CTC world evolved to be control points. Okay, so when you hear interlocking, it's an older term, still applicable in some places, but most times control point is what they're called today in the modern world. So let's start with the railroad crossing a grade. The most primitive form, probably before there were any signal systems, you would have a stop sign, okay, shown on the left, a 4-way stop. Trains would pull up there. In some places in later years, they would toot the horn, make sure there's no opposing movement, and they could go. And, that's all defined in the rule book or in the special instructions. A variation of that would be a swinging gate, again, primitive, not interlocked, nothing automatic about it. There's no man out there, unattended. Then you had the tilting target, okay, on railroads like the B&O. I think N&W used them. Okay, the tilting, horizontal tilt was one route, was good for one route. One route was authorized to go. A tilt would have been the other route. There usually was just one signal. There wasn't a signal for each route. There was a tilting target at the diamond. So manually controlled. I'm not, others might know whether train crews ever moved. My impression is the operators would move them. There'd be an operator there. However, I do think it's possible there's places that they were the train crew actually would operate the tilting target. You notice they have a light on them too. Here's another variation of the first two are non-interlock. This one is non-interlock. This is a picture of Brighton Park. Those semaphores are not interlocked, which means that operator there could line a semaphore into the side of another train. But again, this was a crossing. It's now been, thankfully, it's been made into a remote control interlocking probably close to 10 years ago. But the operator there would line the train. They would come to a stop, and the train would be lined up with a semaphore, and then they'd go. And so a non-interlock crossing at grade. The semaphores were operated by Armstrong levers that you see on the right. Another variation was, and this one was really unique, I think, at least for the Midwest, and that's Pullman Junction. Pullman Junction had a combination of a lot of things. Actually, that tilting target that you saw earlier, that was at Pullman Junction as well on a different diamond. But this diamond here had yellow gates there. I call them fly swatter gates. Okay, they're very flimsy. Operator would position them for the to protect from a movement coming across, protect the opposing routes from traversing. In addition to those flimsy gates, you had flashing lights on the right. You can look at the very top on the right above the CNO to the top right of the CNO had flashing lights there, and that others on this call might be able to tell me what the flashing lights told them, but very unique in that Pullman Junction had just about everything that was ever made. I'm sorry I didn't get to see it. I never got there. I just enjoy it, seeing some of the pictures of it, but an example of a non-interlock crossing at grade. So then after a time, the technology became in the way of relay systems that rail crossings at grade now became interlocked. Okay, the use of shelf, those are called shelf relays on the left. And in the first examples were controlled by a tower. There were other examples where you starting to use relays, starting to interlock them. They would be an automatic interlocking that would be a first come, first serve. Okay. And so you had some of those out there that there was no operator there. It was the first train there would clear the signal. Approach clearing would be another term used for the approach clearing railroad crossing at grade. And finally, in the world today, you've got controlled interlocking crossing at grade where the dispatcher controls it. Oftentimes, supervisory control is employed where the railroads condition their signals. They don't want them to be, their approach cleared, but the dispatcher has to condition his signal to allow the approach clearing to take place. We call that supervisory control. So that's another variation of it. But some places don't have the automatic where it's just strictly a dispatcher. There's no automatic function at all. The dispatcher clears it. The joint facility agreements usually govern that, who's there first and who has the rights. So those things are established by agreement. But this is at Toledo, Ohio, example of a remotely controlled railroad crossing at grade. Predecessor to interlockings, believe it or not, switch tenders were used into the 70s. Okay, maybe even later than that. This one's at Columbus, Ohio. I was fortunate enough to be able to be there observing. In fact, I think the guy there in the picture, I met him one time. This would have been in 1977. Train director in US Tower right there told him what to do, line up a train, told him what track to line, and he'd line it out there, hand line it, and then he once he got it all lined, then he'd wave the flag. And that was permission for the train to proceed. So that's a non-interlocked crossovers. Then going back in time, okay, you had the Armstrong levers, sometimes called the Saxby and Farmer, and that's Marty Bernard. In case anybody in here might know Marty Bernard, he sent me that picture. A railroad photographer, who was an operator back in the day. But those pipelines there, for those of you that aren't familiar, they would move the switches out there. and it was totally mechanically operated. Pull the levers, move the pipes, move the switch, line the signal. The locking bed present in the tower prevented the system from doing anything unsafe. And so those mechanical interlockings, believe it or not, it's only been about 10 years that since the last one was eliminated. I think the one in Springfield, Illinois, Isles, or one of the Springfield towers was the last pipeline tower to go, and it's only been about 10 years. The next improvement from the pipelines, and as I said, the pipelines were from 1890s, and then it wasn't too many years later, early 1900s, that you had the pistol grip was a version. Okay, the locking beds were still there. That's what you see on the right there. That's a locking bed, same as you had with mechanical, but now you had some relays mixed in. So the signal control and switch control was done over relays, but you had a locking bed and you had pistol grips control. We call that electromechanical interlocking. The locking bed, those bars in there that did the locking that prevented signals from being, lined against each other, those bars would be cut by there were special tools that were used to hand cut those bars to get them to lock like that. And it was a very precision type operation to get the locking mechanism, locking bars cut for the locking beds. After locking beds, it became all relay interlockings, okay, which really opened the door to some other things. You could put the control panel there with the line the switches and the signals on the same control panel. But the biggest thing that did, going to an all relay interlocking, was open the door to the ability to take control of that away from a tower and put it in a faraway dispatch center. And that's what was done in 1928 with the very first CTC in the United States. It was Berwick, Ohio, New York Central, where a control point was dispatcher controlled, going back to the late 20s. And that was done by the use of an all relay interlocking. That could not have been done had there been a mechanical locking bed in place. Today, you've got, we'll jump right to the solid state interlockings. There's one on the lower right, which is a mainstay today, remotely controlled by the dispatcher. And picture of the shelter there, the footprints are a lot smaller. There's no relays, very few relays, a couple relays, but not very many. It's all done electronically. And we'll talk about some of the features of these electronic systems. And as I said earlier today, the term you use is control point that I'm familiar with. It. The term interlocking is still out there, but most of the time you're going to call them control points. So let's shift gears and talk about warning systems. And how did you provide warning? The very first warning at grade crossings early on was a flag man. He was out there equipped with a flag. And on the left there, you can watch that video out on the internet of that guy. He's walking back and forth waving that flag. That's a video on the left. That's a still of a video. Pretty interesting, taken from the cab of a locomotive, probably around the turn of the last century. So you had the flagman out there, and then that morphed into the use of the watchman. And the watchman was there to put a sign out there to stop the traffic. Usually on low density highways, okay, on the higher density highways, we'll look at a gate here in a minute, but this guy would walk out there, and he had to walk out there in time for the engine to come, usually pretty slow movements when you use the watchman. Not always, though. Sometimes, I mean, Erie, Pennsylvania had a watchman up until Conrail, up until in the 1990s. There was still a watchman for the nickel plate route through Erie, Pennsylvania. Okay, so here's a picture taken at Leetsdale of a watchman that sits in the shanty there, and his job is to lower that gate electrically. He had to look down the track and make sure he was lowering the gate at the right time. He couldn't be too slow about it because, the trains went pretty fast through there, but that was another form of a watchman. When railroads figured out that there was a whole lot of manual intervention, human factor, they figured out maybe we need to figure out a way to get some track circuits to lower these gates. So that's what this picture is a DC crossing, which was the first type of automation at the crossing signals that to put in DC track circuits, or to use the Wayside Signal System DC track circuits to lower the gates, done with DC relays, shelf relays. You had insulated joints out there, the approaches. You had a fixed location where the crossing signals would begin to activate. So because you had the fixed locations and you required insulated joints, railroads tried to find a way to not have to have insulated joints and to not tie it in with a wayside signal system, and that was by the development of a motion sensing unit. So in the 1960s and into the 70s, railroads came up with motion sensor systems. And these systems did several things to help you. Like I said, they made it so you didn't need insulated joints because you're using audio frequencies rather than the DC track circuits. But the other thing it gave you was that you had the ability to time out. What does that mean? That means if the train stops in the approach, the gates go back up. So that was a great contribution of these motion sensing units, is you implemented the timeout feature. What they lacked though was being able to differentiate between when there were speed discrepancies between fast trains and slow trains. Let's say a passenger train and a coal train, you get a 30-second warning time on the passenger train, but the coal train might have 45 seconds or a minute warning time because it would start in the same place. So how was that addressed? Starting in the early 1990s, the motion sensor morphed into a constant warning device. This device, accomplished with a microprocessor unit, allowed the system to calculate train speed of an approaching train and therefore calculate when the gate needs to come down in order to achieve a 30-second warning time, approximately 30-second warning time. So again, this is called a constant warning time device, and that's the mainstay of what you have out there today. Constant warning time devices. So the passenger train and the coal train get the same warning time, even though one's traveling much faster than the other. So any of these modern systems have a lot of other features that are helpful. They have event recording capability, which is important to establish for troubleshooting, maintenance, and to substantiate if there's allegations about things not working, etc. Remote monitoring capability. They have capability to send back to the office, conditions that the maintainers might want to need to know about, even though, they can't go out there. Conditions like power off or false activation or low battery or gates, broken gate, issues like that. Send information to the back office. Some of them contain redundancy, 2 units, so it stays working if one unit goes down, and aids for maintenance troubleshooting. So you get a lot of new features. Talking about the devices themselves, here's the first crossbuck, and that design changed pretty quick to what you have today. It wasn't retroreflective, and it looked like it was more worried about the cars than what it maybe should have been worried about the locomotive coming there. So that might be the reason why they went to the newer crossbuck. You had crank down gates so that those watchmen you saw earlier, if they had to run, if there was gates at that crossing, he had to be out there cranking that thing. And I hope those counterweights were balanced right, or otherwise he's going to be building up his arm muscles pretty big. It looks pretty heavy, but you can see it was a manual. That was a manual operation early on. We'll see a gate back here in a minute. You had the wigwags. Some of you have probably seen or heard the wigwags. Had quite a few of those in Wisconsin. But they're all just about gone now. What was the disadvantage of a wigwag? They were kind of cute, to get somebody's attention, had something that was moving back and forth. I think the problem with it, I haven't read this, but I'm presuming probably the big drawback of it was that you couldn't aim that light anywhere. You got to be able to, today you have to be able to aim those lights at all the different road configurations. And the wigwag didn't let you do that. Same is true with the Griswold. Okay, nice little sign there that would go stop, but the stop sign would disappear if there's no train around. Okay, but you couldn't really do a whole lot with your road configurations. There's not a lot of flexibility with the Griswold, so they've gone away. You might find one or two of those around Minneapolis, maybe still on some industry track. Griswolds were made in Minneapolis, I think. Here's what you have today. Cantilevers. You have flashing lights. As I mentioned earlier, a lot of different ways flashing lights will be mounted, but very often you have the cantilevers, okay? And very, very often you have the gates. I think the percentage of gated crossings has increased a lot. There's still locations where it doesn't make sense to have gates, but there's not very many locations today. Almost everything that's put in on the state projects has gates. You'll notice that the bell up there, I'm going to talk about the bell in a minute. That one has got a bell up there on the upper right that you can see. So a couple different innovations. One is the use of the LED lights, which has been a big help. That's an LED. You can tell an LED, a light, just like you can with the stop and go lights on the highway. It's got all the little dots there. That's going to be an LED. Okay. LEDs reduce the power consumption, and they help reliability in that, you know, when an incandescent light burns out, the whole unit is dead, but usually the LED is going to go down a little bit at a time. You're going to lose a few LEDs. It's not going to go out all at once. So a couple of advantages there using the LEDs. And then the electronic bell is way on the right. I mentioned earlier is replacing the mechanical bell. They sound just like it. You've got a program, you can't really tell, but you look at it, it's an electronic bell. And to keep you from having to adjust the mechanical clapper all the time. So most people know that, you know, two shorts and a long coming from the locomotive. Okay, that's been the mainstay. That's always going to be, is what it is for warning motorists, right? Okay. Well, that paradigm is shifting a little bit too, in that now you in the quiet zone locations where designated quiet zone, cities can petition to try to reduce the noise of trains going through. One of the things they do is they put up speakers to that emulate a locomotive horn. Believe it or not, okay, that's a locomotive horn noise is coming from those speakers, and the locomotive's not blowing its horn, but it's the speakers that are doing it. And what that's doing for you is that those speakers are pointed down the road, so they're aimed at who the intended people to hear it are, and maybe some of the neighbors are not going to be able to hear it as well. So you're seeing a few of those come out there in the quiet zones. Let's switch and talk about bearing detection. That was a big issue years and years ago when we had a friction bearings on the freight cars that were relying upon proper packing of the waste oil and so forth, that these things heated up quick. And the conductor or the trainman that you see putting his head out of the cupola there, one of the things he's probably doing is he's putting his nose in the air to see if he smells a hot box. Okay, that was one of his jobs. Because if he didn't smell it, it could heat up and start a fire like what you see on the right, or it could be worse. It could be a derailment. So that was one of the functions of the guy in the caboose, was to watch for hot boxes. So we're going to talk about hot box detectors. Starting in the early 1960s, railroads developed hot box detectors that were where a bolometer, electronic sensing device, could be aimed at the bearing area of the bearing, the journal bearing. It could sense it through infrared heat. It could sense if the bearing was hot, even if it was on fire. So these were developed in an effort to try to, again, take the human factor out, and it ended up being pretty successful, which I'll mention here. But where this information went to was by chart recorders to a nearby facility. But what on the left you see the chart recorder that was in a tower, and that was very common to have them either in a tower or a dispatch center, where these hot boxes would be hot box readings. Being when the train goes by the hot box detector, the needle on those chart bearings moves to approximate the heat on the bearing. Okay, and you know the needle would move. If it moved 4 millimeters, it was a cold bearing. If it moved 21 millimeters, it was a hot bearing. So the employees in the towers and in the dispatch centers, part of their job was to decipher that chart there. And if there was a hot box detected, they'd either have to try to call them on the radio, or if they couldn't do that, they'd have to get the local tower or some yardmaster or somebody to tell the train to stop. So that's how that was done. Now on the right, you see what I think might be the only instance of a central hotbox reporting center that was in Atlanta, Georgia for the Southern Railway. All of the hotbox readings on Southern were telemetered into Atlanta, and you had two or three or maybe four hotbox reading guys, 7 by 24. That was their job. to read the charts as they came off quickly. I mean, you can't let them lay around because, you know, for very long, because there's a hot journal out there, trains out there running. You better stop them before there's a derailment. So they had the ability to talk on the radios system wide from Atlanta. So that's what you're looking at there. You're looking at the board of directors getting a tour of the Hotbox Center in Southern in the early 1960s when it was pretty new. Here's one. There might be some people that would recognize this. I recognize this. I remember this an installation just like this up on the Sioux line, just south of Superior. This is a billboard display of a hotbox detector, hotbox detector made by Servo, and it was the job of the conductor in the caboose to look out and see what the billboard told him. And with the combination of lights there, and I couldn't find a special instruction that could tell us on this call what it is that they saw, if it was an all clear signal, what it looked like. But I can tell you, if there was a hot box, the axle number was displayed on the 7-segment display. That's a 7-segment display there that would light up and give him the axle number. And also those lights would tell him what side of the train it was on. And if it was a multiple hot boxes, it would tell that too. So there were 5 lights there, and there was 3 digits of 7-segment display. And some on this call might be able to fill us in a little more on how this worked, but I know SP used them and Sioux Line used them, and it looks like some of the Canadians used them there. So, you know, they were out there. Variations of this, CNNW used a little white light that was placed 2 miles away from the hotbox detector. And if that light, it was a lunar white light, and if it blinked, that meant your train was okay. That was if the dispatcher didn't call them before, okay? Because this is kind of a backup to the dispatcher calling them. If the light was flashing, they'd say light blinking, good to go. If the light wasn't flashing, they had to stop their train and talk to the dispatcher because either the detector didn't work or they had a hot box. So there's various variations. Southern Railway used a rotating beacon mounted on the hot box itself. That engineer would announce, you know, all dark. You know, when the engine goes by, the caboose goes by, he'd announce all dark. Okay, no hot box. So yeah, different ways done on different railroads for the hot boxes. Well, here's the modern hot box, and you can say that the development of the synthesized voice was really a big deal, was a game changer for the railroads because that, along with EOTs, I think you could say, were kind of the keys to getting rid of the caboose. Because when you had synthesized voice, now you could transmit the axle number to the locomotive. Okay, they didn't need anybody in the caboose to do that. And they started in the mid '80s with the voice synthesized voice, and that was a game changer. So that's what you have today. It's a radios transmit out there, and you know you can do a repeat. You can punch in a code and it tells you repeat if you don't hear it. The readings are also in a lot of places are sent now to trending centers on some railroads. The NS has put in a trending center that the information is telemetered into, but the hot box is self-contained. You don't need to have anybody on the caboose and they can get the reading. They can know if they got a hot box. So that's the modern systems. There's also been improvements to the detectors themselves. They went from bolometers to pyrometers, which made them more sensitive, changed the place that they look on the bearing. They can look at inboard scan, outboard scan, different things that they've done to try to make them more accurate. The true stop percentages today are tremendous. It's a very reliable device out there that's not stopping trains unnecessarily like it did, you know, even 10 years ago. So these are really good systems. Draggers have evolved. The earliest draggers used these kind of paddles, which were breakaway. On the right is the picture of the breakaway. It got hit, breakaway, and the maintainer had to come out, and they knew they had an alarm, but they didn't know what axle. Okay, so they had to walk their train if they got an alarm. So the new ones are incorporated in hot box detectors. They're not breakaway. They just restore back to vertical. If they get hit by whatever, low air hose or whatever, they restore back to vertical. The hot box knows what axle happened on. That's broadcasted. Dragging detector indication at axle 242. They know right where to look. course, there's not a north side and south side, but still they know where to look. So that's undergone improvements to keep the trains moving. Here's a picture of a broken flange detector used in a hump yard, okay, detect a wheel problem. They don't really have one of these today. TTCI, which is the research arm of AAR, is still trying to find a way that they could detect broken wheels. And I don't think they found a way yet to do what this finger detector did in the hump yards, and that's detect a broken piece missing out of the flange, off the flange or off the tread. So on the right, that's on the left. On the left, on the right, you see the guy in the hump yard. He's stationed in a pit. He's watching the undercarriage. He's watching for not only broken wheels, but he's looking for brake riggings and other issues. So those were the ways they did wheel defect detection. What you do have today is the Wilds wheel impact load detectors that will detect the whether there's a flat wheel. You know, you used to hear a lot of flat wheels. You're out there watching trains, boom, boom, pound, 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 going by. You don't hear that much anymore. Why not? Because the railroads have installed all wheel impact load detectors on their major lines, on high density lines. And though when a car goes by that has a pound, 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 that information is telemetered into the mechanical offices, and that car is checked out, and the wheel sets are changed out if they need to be. So it's helped out not only with maintenance of cars, but broken rails. A lot of things it's helped. But that's what those are out there. Electronic devices that measured in kips, okay, is what it's measured in. There's kip readings that it reads and decides if it needs to be swapped out now or later. But the other thing it does imbalance loads. If a car is misloaded, you know, too much weight on the right or left, north or south, this device will tell you that too. We'll talk about consist identification. It's evolved quite a bit. It's important for railroads throughout the years to know what cars are where on the railroad. Okay, early on it was a guy standing out in the yard, and he's recording the car initial number going by as the train comes in the yard, and he's giving it to a clerk for transcribing it to go on to company records. Okay, when that was decided to be kind of labor intensive, they came up with ACI, automatic car identification, in the early 70s. That was an optical system. You've probably seen the barcodes on the side of freight cars. They're still out there today. They were put on in the early 70s. But this was an optical system. It would read that barcode, and it would contain the car initial and number, and it was given to a computer. These systems were ultimately unsuccessful. This one's picture was taken at another one at Pullman Junction, my favorite place, that they were ultimately unsuccessful because of, you know, when snow would get on that tag, or grime or whatever, grease, or vandalize, you know, the guy with the spray paint or whatever, you know, you couldn't read it anymore. So what did they go to? Well, in the late 1980s, RFID technology came along, and folks on the railroad said, well, maybe we now have a good way to do this.Maybe we can, all the sites with the ACIs that came out, we'll put in AEI readers. So that's what they did. They equipped the car fleet with, and this was a industry cooperative effort, interoperability. You'll hear that word a number of times. The railroads all work together to come up with a standard for the tags within the industry, within the AAR, standard tag readers, standard tags. Tags were applied to all the rolling stock and locomotives and EOTs. So on both sides. And so the cars can go by these readers. Information goes into the computers so that the information is shared across all the industry. So a car that's destined for Atlanta that goes by a tag reader out at Cheyenne, Wyoming, you know, the customer can see where his car is. You know, even though it's not on NS, you know, the customer that's located on NS can know where the car is at. So that's what these are, using RFID technology, the same technology that you have at your toll plazas there, you know, like in the Illinois toll plaza and so forth, RFID technology. Hump yards. Does anybody know what this is? I can tell you this, it's a kind of a dangerous job. The name of it, the title of that guy is a hump rider. The car is going to be classified. What's he doing? He's riding down the hump. He's on the car. He's going to operate the handbrake. slow it down to the right speed so it doesn't hit too hard on a coupling. Okay, when he gets to the bottom, there's going to be a kind of a shuttle bus that's going to take him back up the top. He's going to do another one. He does that 8 hours a day. He rides that hump, the hump rider. Believe it or not, the hump riders occurred even into the 70s at some places. I think Camden Yard had hump riders into the 70s in Pennsylvania. Columbus, Ohio had them at their yard, 20th Street. What replaced them? Well, the advent of retarders. Retarders were invented in the 20s to squeeze the wheels, slow them down, manually control. The person controlled these retarders, squeezed the wheels and slowed down the cars to the right speed. And this was how classification yards started, was use of retarders to switch them into the right track and switch them to the right speed. So the coupling would be 4 miles an hour or less. In the 60s, the idea was, instead of using manual, why don't we let a computer try to do it? Okay, so that's what they did. This is Selkirk Yard, a picture taken in the 1960s, right after it was built. Now you've got a computer there to control these cars rolling down the hill. You have a master retarder, you got a group retarder, control it into the class track at the right speed. This is what they look like today. They haven't changed really all that much. You know, retarders do the same thing today. The mechanisms have been improved a lot less hardware. You don't have the pumpkin seat and the bell crank and other things. They've made them more efficient. Sensing failure sensing, this kind of thing. And you can see a lot more on the displays on the left of what's going on, overheated mechanisms and so forth, overheated motors. And these can be either air operated or hydraulic, depending on your philosophy. If you want to put in an air plant, you can have them be pneumatic, you know, so they make both. The computer rooms, as anything else, you used to take up a whole floor with the computers, okay? And now you've downsized it to, you know, not much bigger than a desktop computer for a group retarder. So this footprint has gotten a lot smaller, of course, as you can imagine, with a lot more features, a lot cheaper, a lot everything. The displays have changed. They didn't provide a whole lot of information back then, and it was all kind of hard to read, okay? 7-segment display. And now you have it on CRT, lots of information, color coded. You can see just about anything you want. You can see the wheel deck hits. You can see the distance to go is graphically displayed. Everything that you want to know, the weather station, the weights, anything you want, it's seen on that display, and it's interactive. It's changing as the cars are being rolling down the hump. The status of the skate retarder. Speaking of skate retarders, okay, where did we get the name skate retarders? Okay, well, the first skates were actually skates. They were hand skates. And here's a picture of a employee putting down hand skates. And what has he got in his hand? He's got sand. Sand was used to sprinkle on the top of the rail to increase the friction. Because, you know, and these were, remember now, these are 40-foot box cars. These were not heavy cars, but still, you had to have friction to stop the car from rolling when it got to the far end of the class track. You didn't want it to roll out of the clear. So you had a man there whose job was to put sand on the track and to put down the skate retarders whenever a track opened up. Whenever they pull a track, then and now we're going to bring in some new cars, and then you had the first car in had to have this done. Now, after you get first car in, then you don't need to do this anymore. This was just for the leading car, the first car into a class track. So what do we do today? We've got these nice skate retarders here. Then, boy, these things are heavy duty. They can take a 120-ton car and take it going at about double the coupling speed, 8 or 9 miles an hour, and stop it dead stop in the retarder. Pretty nice to have. And, you know, it's very, you know, a lot safer operation than the use of those hand skates.